Hello, everyone. I'm Vitali Braun, and I am sending greetings from Germany across the Atlantic. So it's a lovely afternoon here and the morning for you. I am happy to be part of this session at this Science Summit, and grateful to Robin and Dan that they invited me to be here. Thank you very much also for organizing and sharing that session today. It's an honor for me to be here. And talking about ecology, when we come to my topic today, I want to first highlight that talking about ecology also involves time dimension, which is very important, as all our actions might have ramifications also for generations that are not there yet. And I want to highlight today especially the small debris population that is up there in low Earth orbits, and I will also tell you why this is of importance in a moment. So first of all, some of you might have seen more of the latest news, like some news reached us not so long ago. In fact, for me, it was upon returning from my summer vacation that I found a bunch of emails in my inbox where people started to discuss in what was possibly a debris strike that hit an adapter that you see here on the left image from the Vega launcher. This adapter has a mass of about 100 kilograms, and it was apparently hit by something that was too small to be seen by ground-based sensors. No one saw it coming. And it might have been a meteoroid or a debris. We don't know at this point. But what was even more interesting was that this object that was hit by debris was actually the target of ESA's demonstration mission for active debris removal that we want to go forward with in the next few years. So this mission is currently in the design process, and our member states mandated the agency to perform that mission and demonstrate that we can go up there, grab a piece of debris and bring it down safely. Now it was hit by debris, and we have to reassess the situation. It looks good so far, but there are limiting factors. For instance, if that object would rotate too fast, because if you get a debris strike, there's a certain momentum, and then it implies some torque to that object, and then that object starts tumbling. If that goes too fast, then certain technologies are not able to work well anymore. And so we need to see if the design of the space debris removal mission is still compliant with the target that we have up there. So far it looks good, but it was more a sign, or the way we interpret it, it's a sign of why debris removal is actually important. In first place, the motivation to do debris removal is that we want to avoid in future that larger objects are being hit and then become a source of even more debris up there in space. Another very interesting effect or event happened in 2016. It affected one of our own satellites again, and it was the operational spacecraft Sentinel-1A. It's part of the European Union's Copernicus program, an Earth observation mission. With the SAR antenna that you see on the bottom part of the picture, stretching out a bit below the solar panel. And back then, we received basically some anomaly reports from the involved teams. One was that we lost 5 to 10% of power, and you keep observing the telemetry of that satellite over several revolutions and see that the power is not returning, so it's like a permanent effect, and you write your anomaly report. Another sub-team recorded a similar anomaly, similar in the sense that it was at the same time, for the star trackers that went blind for more than 20 minutes before they recovered again. And then also the orbit determination team came up with a deviation from the nominal orbit of that satellite. It took someone then to put all these different anomaly reports together and build a hypothesis of a debris impact. They approached us as a team of the Space Debris Office of ESA to investigate there. And I took back then in 2016 two of our master students, and we applied basic physics to build that hypothesis of a debris strike in a solar panel. And we presented to the teams later. And one of the engineers, they showed up and said, look, we actually have a camera up there and we can take a picture. And we were surprised because it was the first time that we could actually do something and take direct evidence of what has happened, as we had the camera pointing directly at the point which we hypothesized. And there it was. This is the red arrow that you see here, a 40-centimeter impact feature. And we were able, due to the data and telemetry readings that we had, to also compute that it must have been by a debris impactor of about 1 centimeter in size, causing that damage to our satellite. If that would have happened only milliseconds later, it would have impacted the main body of the satellite, and we would have likely lost the entire mission. And so this triggered a lot of discussions because a 1 centimeter impactor can basically create the damage to destroy your entire satellite. And if we look at this picture, it also shows us how the 1 centimeter debris population looks like. This picture contains the entire history of spaceflight since humans started going into space. And today we speak of about 1 million objects larger than 1 centimeter up there. There are certain structures to it. It's like in many aspects of life where humans go, they leave debris, and then this debris keeps evolving. And that's why you don't see it uniformly distributed in the picture, but it follows certain patterns that then result in this aggregated picture that aggregates in time and over many, many debris generating events. And what is also interesting here is to understand, as Dan has just discussed about the debris population that we mainly focus on with space traffic monitoring, space traffic management, space situational awareness. Usually the discussion is more or less about the cataloged objects. This is what you see on the pie chart here to the right. We discuss, for instance, SpaceX and their Starlink's constellation with thousands of satellites being put out there. But the cataloged population, if we now counterintuitively follow the orange arrow to the left, to the center pie chart, makes only a small part of the entire population of space debris that we think must be up there. And we have strong evidence that I will allude to in the next few slides that basically gives us an understanding of how that environment looks like beyond measurements, even though there is some evidence that allows us to understand this. Now, this 1 million objects larger than 1 centimeter, big enough to cause significant damage and terminate emission, as I said, is also only a small fraction, if you go to the further left, of the about 1 trillion objects that we speak of that are larger than a micron, or in the sub-millimeter regime, as we put it in this graph. So if we speak of space traffic management again, the focus typically is that we want to track and catalog all the objects so we can avoid collisions and basically mitigate the downsides of a contaminated near-Earth space environment. Now, the problem is that there's sensitivity limits with current state-of-the-art and ground-based instruments. We speak of radars and telescopes here. And for a typical satellite in the sun-synchronous orbit, like you see here on the image on the right, this is a Sentinel-2A spacecraft, we can actually only mitigate about 10% of the mission terminating risk. And this is because we can only track objects down to a few centimeters in size. As an engineer, we say usually it's 10 centimeters. But there is a risk that we cannot mitigate. And here we speak of lethal, non-trackable objects that are between 1 centimeter and 10 centimeters. Again, their numbers are in a million, while the trackable population is about 30,000 centimeters. So no matter how many radars or telescopes you put up on ground, you will never reach that region because there's limits to what this technology can achieve from ground. For a typical satellite like Sentinel-2 on this image, it implies that over its mission of 10 years, it accumulates a mission terminating risk of about 6%. A satellite now that's worth several hundreds of millions of dollars. You can imagine what the value of 6% corresponds to if that damage were to occur. And this is interesting to insurers, for instance. But it's also interesting when we start to discuss other aspects like fault or liability, because you cannot attribute who was at fault there, where that impactor came from that destroyed your satellite, because it might have been from previous space activities. And in the case of Sentinel-1A, for instance, the debris piece that hit the solar panel, we were able to tell that it was with a likelihood of 10 to 1 more likely that it was a debris impact of anthropogenic space activity as opposed to a meteoroid strike. So where does all this information actually come from? So how can we learn about space debris that is smaller than what we can actually track from ground? And our master model, to have a first introduction, this is the European space debris reference model. It informs us on several subpopulations of debris, because we know there are certain events that generate space debris, and I will talk about a few of those on the next few slides. But just to give you an idea, we speak here of explosion and collision fragments. Those are the ones that generate usually fragments that are big enough to be tracked from ground. So if you have a collision avoidance maneuver to be performed, most of the time, if it's not an active satellite or a discarded satellite or a rocket stage, it will be one of the many fragments that are a result of explosions that happened in space, or a few of the collisions that we had, like the Cosmos Iridium one in 2009. Now, if we go into a smaller size regime, and here we have two graphs. One on the left is for objects larger than 1 centimeter. On the right, it's objects larger than 1 millimeter. You see different colors. And we speak here of objects, like look at the green graph. It shows you NAK droplets. These are sodium potassium droplets. I will speak about them also later on. But what we see for them is, for instance, that they seem to dominate in a very thin altitude band around 900 kilometers altitude. The x-axis here is altitude. And there we see that it gets into a similar order of magnitude than compared to the fragments that we have. So if you put your spacecraft at 900 kilometers, you will see fragments, but you will also see sodium potassium droplets that are originate in a certain era of space activity that I will also talk about on one of the next slides. We also see solid rocket motor slag particles. These are the yellow graphs. And you see that, for instance, if you go to the 1 millimeter population on the right, that there are certain altitudes, for instance, at 1,000 kilometers, where the solid rocket motor slag, or also the ejecta particles that are generated if something impacts your surface and then it goes out from that crater, are actually the dominating contributions. For the case of Sentinel-1A, when its solar panel got hit, we had 7 tracked fragments that were then became part of the catalog, large enough to be seen. But we assume that there are many more generated that are now out there in space and potentially chasing other satellites without us ever knowing about it. Now, debris impacts have been observed primarily on return surfaces. Like here are 2 examples from the Hubble Space Telescope, or also on the International Space Station by the astronauts that go out on their EVAs. And you see here a collection of images. Problems there are even for the very small impacts, as you can see on the right. They might damage the gloves when the astronauts go over the rail from one point to another. And this is a serious concern up there. And I want to go now a bit back to talk about the actual history, because the problem with small space debris is that it has been always historically underestimated to the extent that we see today. The main discussion is about the big debris, so about collision avoidance and space traffic management. It always relates to the debris that we are able to track from ground and then take action against. Now, there was some evidence collected as early as in the 1970s when Skylab was up there. And they had a particle collector experiment. And then with that experiment, they actually registered some impact. And it was then analyzed on ground, and they found that the impactor shows a titanium signature. The hypothesis was built that this particle with titanium must have resulted somewhere outside our solar system, because there was no other explanation for this. Only later, an alternative hypothesis emerged that this titanium particle is actually a result of paints paints that were formerly on the outer surfaces of satellites or rocket stages that have been brought into space and started to age, being exposed to that environment, and then paint is being released, and then those paint chips start impacting surfaces of other satellites. Again, too small to be seen, and this is maybe also the reason why back then there were not many believers in a substantial small debris population that nobody was actually able to see. An interesting event happened then a bit later in 1977, when the Soviets were operating a series of radar ocean reconnaissance satellites. This was done on both sides during the Cold War by the US and the Soviets. They operated these satellites to have radars above the ocean and then basically screen the entire ocean for naval traffic. So both sides were pretty much informed about what was going on the Atlantic due to those satellites. For the Soviet program, but also for the US one, they employed a nuclear reactor on board with uranium-235, because radars to illuminate the entire ocean actually need a lot of power. And you want them to fly very low so that you have a higher resolution. But if you fly very low, there's a lot of residual drag. So if you put huge solar panels, which were not that mature back then, you also have a problem that your satellite will not live for too long up there. So they had nuclear reactors. And then one incident happened in 1978. One of them failed on the Soviet side, and it started to do erratic maneuvers in December 1977. This was spotted by the US in their regular radar observations of the target. And they were in consultation with the Soviets back then, and they realized this thing is going to come down through Earth's atmosphere, a whole nuclear reactor in an uncontrolled manner. And what happened later was that this reactor basically came down over a large swath in North America, over Canada. And it also distributed a lot of radioactive material, because the reactor core is actually designed to withstand a lot of pressure and heat, which is what you experience during the atmospheric re-entry. And so this nuclear material basically came down in a very much unharmed condition. A search team was built, and this was called an Operation Morning Light. You see it on the left pictures. They had to react very fast, because searching those pieces meant that you can do it very well in the winter months, where there's a huge contrast due to the snow coverage. So they went there and tried to find the pieces from that re-entry, and they did. In fact, one of the pieces had so much radioactivity that being exposed to it or being close to it for a couple of hours meant that you would absorb a lethal dose of radioactivity. So this was a major incident, and that, in fact, one of the few cases where the liability convention was triggered. The Soviets paid basically some of the expenses that were needed to run this Operation Morning Light to recover those pieces. But what happened in orbit later was that the Soviets, of course, came up with a solution to mitigate such an effect. And one of the aspects was that these satellites, when the malfunction would happen, would automatically transition to a higher orbit, sufficiently high orbit. They called it at 900 kilometers altitude. And at that altitude, they would eject the reactor cone. Now you have the fuel rods basically exposed into space. And if they would come down in 300 years from now, they would basically burn up and distribute the radioactive elements in the higher atmosphere layers. What also happened during this reactor core ejection event was that a lot of sodium-potassium droplets, being the primary coolant of that reactor, were also released because this coolant loop was opened. Scientists believed back then that those sodium-potassium droplets or sodium-potassium as the alloy they used for cooling would evaporate, but it didn't. It turned out they formed perfect metallic spheres. And they are, since the 80s, still out there. Many of these reactor core ejection events happened, and we see them also in our routine daily collision avoidance, for instance, for our ESA satellites. You can monitor them very well because they're metallic spheres. They are the perfect radar targets. You can always know whether I'm observing now a sodium-potassium droplet or another fragment just by the signature that they leave behind. what was then interesting in the 1980s was that the space shuttle brought an experiment carrier, which is called the long duration exposure facility, up into space. It was meant to stay for 1 year, but then due to problems in the shuttle program, like the Challenger catastrophe later in 1986, it remained in space for 6 years in total. And the idea was that you have, as you see here in the picture, many different experimental racks where you can do material science, but also some of them were part of the interplanetary dust experiment. These were sensitive surfaces that were time tagging kinetic impact events. And what happened was, if you look at the right crosses in this graph now on the left, that several days after the deployment of this platform, there were a lot of impacts registered. In fact, this huge clustering of objects that you see on the left of this graph was due to 2 solid rocket motor firings that happened in the very same period, coincidentally. These were 2 failed satellites, Wester 6 and Palapa B2. They were later recovered by the space shuttle, brought back to Earth, refurbished, and relaunched again because they were insured for doing that. They tasked NASA to do this, and in fact, this was the first, what one could say, the active debris removal mission, and then maintain a satellite again and launch it again in 1984. What was interesting, though, was that we could later correlate this solid rocket motor firings, which creates dust and slag particles when that motor burns, and they are ejected into orbit and start revolving around Earth too. And then they would impact the LDEF experiment, which had its orbit elsewhere. And we were able to model this by using our solid rocket motor firing model. And this graph shows you basically the correlation with the blue circles with the actual data that are the red crosses. Now you see also there's other cluster events that we saw in that data. And it was interesting because at that time, no one was able to understand why there are additional clusters. No one knew where they came from. This is what you see now designated with Cosmos 1551 or 57 or 73. This happened only in the early 2000s, so in the first decade of our century, that one scientist at the University of Braunschweig, and I was happy to meet him too at that time, he basically took Soviet photo reconnaissance satellites, retro firings. These were photo capsules that were returning to Earth to deliver the film that was then developed so that they can gather intelligence data. And those capsules, they were always firing at a certain latitude so that they can re-enter over Siberia and be recovered. And he modeled what we knew of must have been those events. There were hundreds of individual events, and compiled a database of those. We modeled each and every single one of them. And later he also analyzed whether they correlated with certain surfaces that were exposed to space or not. And in LDEF, we found exactly this. We could suddenly explain certain impact features that were observed for the return surfaces from LDEF that before we were not able to observe. And we had then direct evidence even that these solid rocket motor firings must have happened as a kind of validation of our model assumptions that the small debris is actually up there. And then there's the Hubble Space Telescope. It's another interesting example because Hubble was a cooperation between NASA and ESA. It was launched in 1990, and ESA contributed the solar panels that you see here in that image. The problem with those solar panels, as it turned out after some point, was that due to the thermal effects, there was some cracking. It resulted in some oscillations, and so the optics were not properly working for Hubble. Those images that we got to know, got familiar with later on, they wouldn't have been possible with those solar panels. But of course, also Hubble suffered another problem, which was the primary mirror that had very blurry images. So the space shuttle went up there to install the corrective optics. At the same time, they also replaced the solar panels, and they were brought back to Earth and analyzed again. These were ESA solar panels, so NASA returned them to us. We took them in the lab and started counting the craters after 3 years of exposure. In fact, a second mission took also place to do it in 2001 again. The space shuttle went up there, they removed again the solar panels, and then we had many, many years of accumulated craters that we could count. And we put them again into our model. And what you see in this chart on the right, we have the debris data and the meteorites data. We were even able to discriminate between whether an impact feature is by meteorite or debris by studying the material composition in those craters. You see the two lines, the orange ones and the blue ones for the black ones, the black triangles for the meteoroids. But then there's our model, which is the gray dotted line that you see there. And if you compare it to the debris, you see there's an interesting change in the slope of the curve at about 10 to the minus 4 meters in the conchoidal fracture diameter. It's basically the diameter of a crater for a brittle surface. And this is something that results out from the model when we do it source-wise. And if we model solid rocket motor dust contributions, it is mainly basically the steep increase in debris particles below a few microns, where the solid rocket motor dust population is dominating. So for our work, it's basically quite relevant to have those surfaces that return to Earth, because they provide us with evidence of space activity and small debris contamination that's happening in space. And we can even, as I showed you with the examples in LDEF, trace it back to specific events or solid rocket motor firings that happened in space. Now, that was very much in the 1990s or 80s, but if we look also at this graph, we produce an annual report, and this is from the latest one, 2023, that you can access for free. It also shows you that, this era is not over yet. So there are still solid rocket motors that are being used. They eject those particles, for instance. And we have to be mindful of these contamination effects that happen, especially also if we continue space exploration and go into other areas. They will remain always too small to be seen, but they have impact on our missions. And this is something that we have to discuss about. And this is also something now that I would like to finish with. And thank you all for your attention. And I'm also ready or still here to discuss any questions. Thank you.